All right, good morning, everyone. So we'll get started again. Homework number 9 is due tomorrow by midnight. Okay, so make sure you finish them by tomorrow midnight. You'll get a final reminder tomorrow on a lecture. So exam 3 was scheduled on Friday, so that's the current plan. But we'll see what the school decide this afternoon to see if we are going online this week or returning back to in seat this week. Okay, so if we are going to be in seat, then we can have exam on Friday, okay, in seat. And then if we are going online for just 1 week, we can probably postpone the exam to be sometime next week to be in seat. But there's a chance that we might be going full online for the remainder of the semester. Then we'll have to see how the exam will be conducted in that case. Okay, I will look into some options we have. So one of the things you guys might have been trying this in other classes already, but we'll be using the respondents lockdown mode for the online exam. But we'll talk about that later, depending on what the school decide to do from next week and then for the remainder of the semester. Okay, so um, you'll be updated on the exam. Um, Probably tomorrow we'll see that what the school decides today. Okay. Um, so today we'll be checking on chapter 12 on static equilibrium, and then a little bit on elasticity at the end of this chapter. So I think some of you guys are taking statics, and then also some of you may have taken it already, but we'll just briefly mention for the static equilibrium here. Okay, so for if the object in equilibrium, that means the net force is equal to 0. Now, depending on if the object is moving or not, if it's not moving, then it's in static equilibrium. Okay, so if an object is at rest, then it's in static equilibrium. Then the first condition for static equilibrium would be net force equal to 0. Okay, if this is two-dimensional scenario, then you will have net force equal to in x equal to 0. You will also have net force in y equal to 0. Okay, you can expand this into three-dimensional net force in z should be equal to 0 if that's the case. Okay. All right, so that's the first condition. Net force should be equal to 0. All right. Now, if the object, the net force on the object is equal to 0, but the object is moving, then it's in static or it's in dynamic equilibrium because it's moving. So in this scenario, if the car is moving with a constant velocity, that means net force is equal to 0. So then in x direction, the force applied to the wheels, the static friction, that should be equal to any resistance force that the car receives, mostly like air resistance. Okay, so those two should cancel out. The weight in vertical direction should balance out the normal force applied to the tires. Okay, so those will cancel out. But because it's moving, so it's in dynamic equilibrium. All right. So now net force equal to 0. So in the case that the two forces are along one line, so that means they are acting at the same point over here, then they cancel out each other. Okay, so that's in static equilibrium. But however, if you apply force at different locations on the object, for this case, again, the hockey stick over here, then even though these two net force will cancel out, right? But the hockey stick will still rotate with an x rotation. So then that tells you that net force equal to 0 is not necessarily the sufficient condition for achieving static equilibrium. Okay, so then there has to be a second condition here in addition to the first condition. Okay, so that second condition would be net torque equal to 0. So net torque for all the forces on the object should be 0 in order to achieve static equilibrium. Okay, so if you have the two conditions satisfied, then the object will be in static equilibrium. Okay, so net force equal to 0 and then net torque equal to 0. Okay. To give you an example, if you go to the playground where there's a seesaw. If two children are sitting on both sides, either side of the seesaw, then you will see that if at the moment it's in equilibrium, the seesaw is in equilibrium, then there are three forces on the seesaw. There's the weights of the two children, and then the supporting force through the pivot point over here. Okay, so those three forces should add up to be 0. Now those forces are all in the y direction, so the net force is just in y direction. They should add up to be 0. Okay, net torque should be also equal to 0. The seesaw is rotating with the pivot point over here. So then torque by weight 1, it's making this seesaw going counterclockwise, so that's positive torque. And then torque by weight 2, W2, is making the seesaw going in the clockwise direction, so that's negative. So torque by W1 minus torque by W2 should be equal to 0. Now torque by this supporting force F sub P, that should be 0 because the seesaw is rotating with the pivot point. So then R for this F sub P is 0. So that guy doesn't have a contributing the torque into the system here. Okay, so you only see two torques here because this third force here is having a torque of 0 because the distance R is 0. Okay. Now if your system is in equilibrium, in the sense that net torque is also equal to 0. So for example, as the child sitting on a plank with both ends being supported by the parent. So then there are three forces on the plank over here, F1, F2, and then mg. Okay, and total torque on the plank should be also 0. Okay, so in that sense, the x rotation, because it's not obvious that which point is the x rotation going through, so you can pick any point to be x rotation if net torque is equal to 0. Okay, you can pick at this point to be x rotation, or the other end of the plank to be x rotation, or you can pick any point in between. Okay, it doesn't really matter. Now, the rule of thumb is you want to pick an axis rotation that goes through the action point of a force. Okay, and then in some cases, if there are multiple forces acting on that particular point, then that might be your axis rotation, because then you eliminated a couple of torques by picking your axis rotation. Okay. All right. We will take a look on this example here. So there were several examples in this section, but we'll pick this one, and then you guys can check the rest by yourself. Okay. So this one says, to determine the location of her center of mass, a physics student lies on a lightweight plank supported by two scales, 2.50 meters apart. As indicated in the figure, if the left scale reads 435 newtons and the right scale reads 183 newtons, find the student's mass, and B, the distance from the student's head to her center of mass. Okay, so find her mass and then find center of mass. So basically, the plank is in static equilibrium, so you can apply net force equal to 0, and then you can apply net torque equal to 0. Okay, and you should be able to solve for the mass and the center of mass. All right, I'll have you guys work on this, and then we can take a look at the solution in a few seconds here together. All right, so let's take a look here together. So the two conditions to apply here, the net force equal to 0 and net torque equal to 0, okay? Um, so those three forces, N1, N2, and Mg, they are all in vertical direction. So I'm going to just focus on the vertical direction, okay? So net force should be N1 plus M2 because those two are in the upward direction and Mg is in the downward direction. That should equal to 0, okay? So this is the result of net force equal to 0. And then net torque equal to 0, you apply that because this is instead equilibrium, that means net torque is equal to 0, so you can pick any point to be your axis rotation. I'm going to take where N1 is applied to the axis to be the axis rotation, okay? So then I will have just torque by this force N2 and then Mg. Torque by N1 will be equal to 0 because it's at the axis rotation, okay? So then N2 times the 2.5 meters, right? And that makes this guy rotate counterclockwise. This mg will make it rotate clockwise. So minus mg times the what we are looking for, the center of mass. Okay, x center of mass, that equal to 0. Okay, so you basically have two equations. You have two unknowns to solve, m and then the center of mass measured from the head of the student. Okay. This would be your x center of mass. All right. From the first equation, basically you can solve for m because n1, n2 are given, g is the 9.8. So then from first equation, it will tell you n1 plus n2 is equal to mg, right? So then divide both sides by g to give you the m. So 435 newtons plus 183 newtons divided by 9.8 meters per second square. That will be your mass. It's 63.1 kilogram for the mass. Okay, now from the second equation, now you can solve your x center of mass. Okay, so this minus that equal to 0. That means n2 will be 183 newtons times 2.5 meters equals to mg. You can take n1 plus n2 to be mg, or you can use this guy. Okay, so 63.1 kilogram times the 9.8 meters per second square times x center of mass. Okay, and divide both sides by this. Will give you your center of mass. Okay, so that gives you 0.740 meters as the center of mass of the student measured from her head. Okay, all right, and then I did see you guys put in the correct answers for the responses. That's good. Okay, so let me update with you guys. I just got an email from the academic affairs says we are going to return to face-to-face instruction from tomorrow. Okay, so then basically I think we are going to have the exam on Friday in person. I know there's a student in quarantine, so you can make up your exam when you return. Okay, so keep in mind you'll be having a different version of the exam as the ones that taken in person, just to be fair. Okay, all right. Also, let me know if you have questions on this example here before we move on. Okay, so if that's clear, let's move on here. So the example we took a look at was one-dimensional example because the forces are all in one dimension. Now chances are you are going to see forces also in x and in two-dimensional. That means there's an x direction and then there's a y direction. So if that's the case, then you are going to do net force in x direction, and then also going to do net force in y direction. Both should be equal to 0 if the object or system is in static equilibrium. Okay, so for that, let's take a look on this example over here. It says a 65-kilogram person stands on a lightweight ladder, as shown in the sketch here. The floor is rough, hence it exerts both a normal force F1 and a frictional force F2 on the ladder. The wall, on the other hand, is frictionless. It exerts only a normal force F3. Using the dimensions given in the figure, find magnitudes of F1, F2, and F3. Okay, so basically you are going to apply net force in x direction equal to 0. You are going to also apply net force in y direction going to be 0. And then you are going to use net torque equal to 0. Okay, use those three equations, and then you will solve for three unknowns, F1, F2, and F3. Okay, so give it a try. Again, we can take a look on this one together in a few minutes. Okay. All right, so let's take a look here together. I see a few responses in. Okay. Um, so as I mentioned, you should apply net force equal to 0, and then also net torque equal to 0. Okay, so net force goes to 0. This is two-dimensional, so that means net force in x direction equals to 0. Net force in y direction equals to 0. Okay, and then also net torque should be equal to 0. All right, so there are four forces, two in x direction, two in y direction. Okay, so in x direction, you'll have this F2, that's positive direction, F1 is negative. So F2 minus F1 goes to 0. In the y direction, F3 is positive, mg is negative. So F3 minus mg equals to 0. Okay, now net torque equal to 0. At the bottom of letters here, you have two forces acting on that point. So you can pick that x, your axis rotation. Okay, so then you can actually have two forces that have 0 torque. So only I have two torques by this one and then by that one. Okay, so F1 will make this guy rotate clockwise or counterclockwise. So that's positive torque, and mg will make the ladder rotate clockwise. That's negative torque. Okay. So for F1 minus R, okay, so remember it will be R times F times the sine of theta. Okay, so if you are doing RF sine, so this is the angle theta between the two. Okay, between this is R, this is F, so this is theta. So this angle is the same as this angle. Okay, so if you are doing this total length times sine theta, that would be actually this guy. Okay, the A, so it would be A times F1. That's torque by F1, and then minus for mg over here, you are going to take this as your force, right? And then this is the r distance from here to there to where the mg is applied. That's your r, but you'll be doing r mg, this guy, right? Theta. So and it will be like RMG theta, sine theta. So sine theta will be B. Okay, so that's the geometry there. So then minus B mg, that goes to 0. Okay, I think that might be the difficult part there for geometry there. Okay. But then after that is determined, you have three equations. Okay, then F1, F2, and F3 are the unknowns. The rest are known numbers. You can solve for three unknowns from there. Okay. Basically, you can start from, so from equation 1, that tells you F2 is going to be equal to F1, okay? Just magnitude-wise. From F3, it tells you F3 is equal to mg, okay? So then F3 can be calculated directly. That's mg. So F3, you can do mg. That gives you F3. So 65 kilogram times 9.8 meters per second square, okay? To be 637 newtons. Okay, so that's F3.
Excuse
I
me.
can turn to this equation, the third equation, to calculate F1, which would be also F2. Okay, because F2 equals to F1. So from here, you can see AF1 is equal to B times mg. Okay, so then F1 equals to BmG over A, which is B is 0.7, 0.70 meters times mg. Mg will be 637 newtons divided by A, 3.8 meters. Okay, so that gives you roughly 117 newtons. So this is F1 and then also F2. Okay. Yeah, so there's a chat saying the force pointing in the positive y should be F1. Okay, so yeah, so you're right. In the figure, original figure, that's F1. Yeah, I didn't follow the notation over there, but okay, so this is the original F1. Let's make clear. This is original F1. This is original F3. and then that's the original F2. Okay, F2 was right. I kind of swapped the F1 F3. Okay, so then F3, or in this case F2 equals to F3. So the final answer should be F1 equals to 637. F2 equals to F3 equals to 117 newtons. Okay, sorry for my inconsistent notation with the original problem. Okay, so, and thanks for pointing that out. All right. Okay. Any other questions you guys might have? All right. So if not, there's a couple more example. We'll see if we can finish both of them or maybe just one of them. Okay. So the next example here, so there's this weights in the pen here. So you kind of adding like many pieces of different weights over here gradually until this wheel of mass already is pulled over the obstacle of height d, okay, as showing in the figure over here. Now, what's the minimum mass of weights plus the pen needed to accomplish this? Okay, so given that this mass, the wheel of mass is capital mass, capital M, that's given, the radius r is given, and then d is given. What would be the pen and the mass together? Okay, so that this guy just start to move. Okay, so again, I'll have you guys try to solve for this, and then we can take a look on the solutions together in a few minutes here. Okay. All right, so let's take a look here. Okay, so when this wheel is being pulled, that is just started to encounter this barrier, that means the contact over here has no supporting force, right? Initially it might have supporting force at mg, but gradually as this pulls over here, when you're adding the weights over here, so then that more force gradually decrease at the point when it just becomes zero, then it starts to overcome this obstacle, right? So that's the condition over here. So then on this wheel, you'll see that's mg, capital Mg. There will be this pulling force, T, tension. There will be this force, okay, at the contact point. So probably something like normal force, another normal force, M prime, or you can say N1 or N2, whatever. But let's take this as your x rotation, okay? So x is our rotation. So then talk by this guy, supporting force from this point will be zero, right? Because R is equal to zero. So basically, there we talk by this tension force, there will be talk by this weight, okay? Those two should cancel out, all right? So net torque should cancel out in that sense. So then it will be mg times R times, so mg goes down, R goes in that direction, times up sine of this angle, okay? So then capital M G times R times sine of theta should equal to tension force, all right? And then this is R, so tension goes that way, this is R, and then this angle, we can call it phi, okay? Or which would be like 90 degrees minus theta, okay? So that would be tension times R times sine of 90 degree minus theta, okay? Because this should be, the two angles should add up to be 90, okay? So then that become cosine theta, right? Sine of 90 minus theta is cosine theta. So the tension here should be equal to the mg, right? This guy here, because you are gradually adding that, so it's not moving. So then these two should equal to each other, okay? So there's no oscillation, these two should equal to each other, okay? So you can replace T as mg. So small mg times R times cosine theta equals to capital mgr sine of theta, right? So then G and R cancel out G and R here. You can move this guy to the other side of the equation, divide by cosine. So then small m is equal to capital M times tangent of theta, okay? So m, tangent of theta is your small m then. But theta is not given, right, as an unknown. So theta, you want to express tangent theta. Tangent theta will be this guy, will be this length over this, right? This over here is the total R minus this part of D, okay? And then this would be, you're looking at this right angle triangle. So let me just draw it on this side. So this is R, this is R minus D on this side. This is the theta, okay? So tangent theta will be this side. This side is going to be square root of the hypotenuse square minus this square, R minus D square, okay? So then tangent theta here will be equal to this side over that side. So square root of R squared minus R minus D squared divided by R minus D. Okay. So you can express in that way. So capital M times square root of R squared minus R minus D squared divided by R minus D. That's your math. Okay, so this is the final answer. It's not given in any numbers, but you can express the mass in terms of given quantities. Okay. All right. Any questions you guys might have? All right. So if not, I think for the next one, we probably don't have time for the full solution, but we'll check to get you guys started, and then you guys probably can finish that.
Excuse me.
Yourself.
Excuse me.
Okay. So there's a cram here.
Excuse me, Dr. Ho.
This spoon is 12.0 meters from A to B. Okay, so let's see. Okay, this is point A over here. This is A, this is B over there. There's this point. And this is connect over there. There'll be tension here. This angle is 10 degrees. And then this angle is 30 degrees. It's this weight. I'm gonna call this capital M. Okay, so capital MG. That's the weight down there. All right. So that's the tension over here, T. That will be, the bone itself will be having a small mass. Okay, so small m. I'm going to use small m. So it's at geometry center. So that means somewhere in the middle here, small mg. That's this force over here. I'm going to just make the x component and y component. Okay, fx over here and then fy there at point A. Okay, so at point A, you can resolve the force into x and y component. So it's probably going to be like somewhere there. That's the force, but resolve it in x and y components. Okay, so that will be tension, small mg, capital Mg. Okay, and this guy. All right. So in this case over here, so tension is not exactly equal to this. Okay, because this is in reality, you're not going to have a perfect pulley at this point B. Okay, so it's likely tension is not going to be equal to that. Okay, all right, but we can take a look. We can take a look the bone here as the object of interest. So there's this force, tension force. There's this mg. There's this mg. There's this. Okay, so 1, 2, 3, 4, 5. 5 forces. Now for the tension, you can resolve it to x and y direction as well. Okay, so the horizontal direction over here. Okay, so if this is 10 degree, this is 30 degree. So that means this angle is 20 degree. Okay, with respect to the horizontal, but I'm not drawing it into according to the scale, but that's what it should be. Okay, so tension then will be having a tension x, tension y in that direction. So you can resolve tension into the two components. Okay. All right. So then you apply net force equal to 0. You're going to say net force in x is equal to 0, which means net force in x is this guy, Fx. Okay. Minus tension force x. Tension x will be T cosine of this 20. Okay. Cosine of 20 degrees. That equals to 0. All right. Net force in y direction should also equal to 0. So you have 1, 2, 3, and 4. Okay, so Fy minus small mg minus capital Mg minus tension y, Ty, that will be T sine of 20 degree. That goes to 0. Okay, so 2 equations, and then the third equation will be net force equal to net torque equal to 0. Okay, so I think the best way to do it is to take this as your x rotation, this point as your x rotation. Okay, so then you'll have this, this, and this. Okay, so you can set up that, or you can have, let me see, or you can have like this two together and then that one. Okay, it doesn't matter. Let me just use 3 forces. Okay, so I'm going to use tension as the combination of x and y component here. So tension here, T times the length, total length L. Okay, all right. Think I have unstable internet, but basically set up those 3 equations. Okay, and then the 3 unknowns are fx, fy, and then t. And then you plug in your numbers, you should be able to solve for the 3 unknowns. Okay, so at the end, t is equal to 171062 newtons, fx is equal to 160747 newtons, and fy is equal to 97707 newtons. Okay, this is what you will get at the end. All right, so then the angle for force, you can also for F, you can also calculate tangent inverse of Fy over Fx. Okay, that's going to be 31.29 degrees. Okay, all right, so I think I ran over a little bit, 1 minute. So again, tomorrow for this class, we'll meet online only because that's all what we had usually. So, but for your other classes, you might have to return to in person. Okay, if you are not in quarantine. So we'll return in person on Wednesday for this class. Okay, and then you guys should have lab tomorrow as well. Okay, so I'll see you guys tomorrow in the lecture then. Bye bye.